How's it going, guys? So welcome to our first recording where we will be reviewing functions. Now before we get to that though, I want to talk a little bit about what is calculus and how is it different from the other math courses that we've taken before. Well, I like to think about calculus as the mathematics of change, for example velocities and accelerations. It's also the mathematics of tangent lines, slopes, a topic that hopefully we're quite a bit familiar, areas, volumes, and so forth, and a variety of other concepts that have enabled scientists, engineers, and economists to model real-life situations. And that's why we like math, right? Because it allows us to do some modeling. Now, although in pre-calculus mathematics, we've also dealt with velocities, accelerations, tangent lines, slopes, and so on, there's a fundamental difference between pre-calculus and calculus. Now, pre-calculus mathematics, they're more statics, whereas calculus is more dynamics. So for example, let's say that you're dealing with an object that's traveling at a constant velocity. Now that can be analyzed with pre-calculus, but in order to analyze the velocity of an accelerating object, you need calculus. Now another example for it, say, is the slope of a line. It can be analyzed with pre-calculus mathematics. We've done that before, the rise over the run. But in order to analyze the slope of a curve, we need calculus. Another big example is we can get the area of rectangles or any other geometric shape with pre-calculus, but in order to analyze the area underneath a general curve, we will need calculus. Now, one particular example that I like, and this is what we're going to be seeing right now, is that we can get the height of a function with pre-calculus, but in order to get the maximum height for a curve on a given interval, we need calculus. And this is the example that I want to begin with right now. So let's begin with the algebra problem. Let's say that we have a cardboard box with a square base that can contain a volume of 400 inches cubed. Now if the height of the box is twice the length of the base, let's go ahead and find the dimensions of the box. So here I've drawn the little box right now. I'm not too good sketching, as you guys will see in class later, but here it is. I use OneNote to help me draw it. Alright, so I don't know if anyone remembers, but the volume of a box is the length times the width times the height. Okay, now what is this problem telling us? We're being told that the box has a square base, so that means that the length and the width, they are equal to each other if you want a square base. I'm just going to finish throwing this here. There we go. Alright, so square base means that the length is equals to the width. And we also know that the height, let's see, the height here is twice the length of the base. Alright, so if we define the length of the base to be L right now, then the height, which I'll keep on using plumb, is 2 times the length. Okay, so this is what the problem is telling us, and we know that the volume has to contain 400 inches cubed. Alright, so putting everything together, then our volume is going to be the length times the width, which we know they're equal because of the fact that it's a square base, times the height, which we know it's twice the length, so times 2L, and that should be equals to 400 inches cubed. Okay, so simplifying the process a little bit here, we have L times 2L. Now you gotta be careful here, guys. I know it might seem a little bit easy, but I often encounter different answers for this one. So right now we have 3 lengths, so we should have an L cubed because it's multiplying by itself 3 times, and we also have the 2 right here, so that's 2L cubed is equals to 400. Okay, so we can figure out, okay, what has to be the length. So let's solve for L. Divide by 2, divide by 2, so we get L cubed is equals to 200. Alrighty, now we can go ahead and take the cube root. So L cubed is equals to 200. Cube root, cancel, cancel. But if we take the cube root on one side, we got to take the cube root of the other. So there we go. The length should be equals to whatever the cube root of 200 is. I don't know what exactly it is, but it's just some number. So the length is the cube root of 200 inches. Let's not forget our units. Okay, so this one here hopefully wasn't too bad. We had to read the problem carefully to recognize what it meant with the square base, and we were given the height to be twice the length. So that was enough to help us solve the problem. Now, how does this compare to a calculus problem? Well, let's read the calculus problem. So the calculus problem says that, okay, you have a closed rectangular container with a square base, and that is to have a volume of 400 inches cubed. Now, the material for the top and the bottom of the container will cost $2 per inch squared, and the material for the sides will cost $5 per inch squared. And we want to go ahead and find the dimensions of the container that will have the least cost. So notice how the wording here is different. Now we want to have the least amount of cost. So graphically, if you picture the graph, we are looking for the minimum value or the lowest value in a graph. Now, I'm not sure if this is how it's going to be looking exactly, but that is the idea. So let's say that we happen to know that the cost is given by the following function or equation here, that the cost as a function of x, where x is the length of the box, is 4x squared plus 8,000 over x. We have the equation. How do we find the least cost? How do we find the minimum? Well, multiple ways that we can do it. We could graph it if we happen to have a graphing calculator, or alternatively, we can just put it in a table of values and see what values for the cost do you get for different x's, and that's exactly what I do here. So we see here a table of values where I try different values for x, the length. Now the height, don't worry about how I'm getting it here. It's trade secrets, I would say. But we get to see how the cost is changing as the x changes. So when the length was 1 inch, the cost was 8,000. When the length was 5 inches, then the cost was 1,700. And it seems like the cost is going down until we reach a length of 10 inches. Now, when the length is 10 inches, it looks like our cost is 1,200 here. Now, if I keep on increasing the length of the base of the box to 11, 12, 13, 14, you do see that the price starts to go up again. So it does seem like when x is 10 inches, you are minimizing the cost to 1,200. But there's a flaw here, because I'm increasing the length of the box, of the base of the box, by 1 unit intervals from 1 to 2, 3, 4, 5, and so forth. But how do I know that it's exactly at 10 inches? What if I try 10.5 inches or 10.7 inches? What if that is actually the minimum value? Because it could be. Now, fortunately for us though, the value for 10 is actually the minimum value, but in a couple of weeks, we'll be able to confidently answer this type of questions. In the meantime though, let's review a little bit of functions.